Hello and welcome to the Evolution and Meta-heuristic Optimization in Engineering, Scalar and Multi-Objective Approach course. This module will regard the scalar equivalent formulation for multi-objective optimization. So for what concerns the context of this video, we will try to understand how to formulate a multi-objective criterion in a scalar equivalent one, where multiple objectives are some way combined into one equivalent value. Then we will introduce some of the ways that we can do this, so by weighted sum of objective, goal programming, fuzzy membership function aggregation, and by means of some game theoretic approach. We will end this video trying to summarize the pros and cons of each approach to understand how we can use these approaches. So let's start from the weighted sum of objectives. As we have seen in the previous video, we are given a multi-objective optimization problem with some objective, OK, K going from 1 to capital M, and we want to combine this objective in one single objective O, trying to make a weighted sum of all the objectives. So we make a sum from K from 1 to capital M of the product of W sub K, a constant weight, multiplied by the value of the object. The weights are supposed to be all positive. Now, why do we need weights? They have twofold purposes. First, normalization. It is not possible to sum quantities that do not have the same physical units. And then they can also be used to define an order of priority among the objectives. So let's try to see this with an example. We have an electrical motor, and while the electrical motor is working, it is getting warmed up. So we have a problem where we want to minimize the highest temperature within the motor, and we know that the maximum temperature is 180 degrees Celsius. And then we want to minimize at the same time also the weight, and we know in advance that the maximum weight will be a allowable weight of 75 kilos. So what we can do, we have two objectives, one is temperature and one is the weight. So we cannot sum degrees with kilograms, but what we can is normalize the values. If the temperature value is 160 degrees, we normalize by the maximum value, that is, we get a normalized value of temperature that is 160 degrees divided by the maximum 180. So we get one number, this is 0.89, that is dimensionless, and we call it tau. We can do the same with the weight, so 70 kilos divided by 75 is our maximum value is 0.93. And so now we could, in principle, sum these two numbers. But then we want to do another thing. So for instance, let's say that we want to give to the temperature a higher priority. So let's say that we want to give 70% of the importance to the objective of the temperature and 30% to the weight. To do this, we define a value alpha that is 0.7, so 70%. And we make the sum of the objective alpha times tau. So the normalized value of the temperature plus 1 minus alpha times omega, that is the normalized value of weight. So in the end, what we have is that for this particular configuration, we have a 0.9 value. So this can be compared with other configuration and try to go to the minimum. If we are going to look at the value of the weights, we have to see that the temperature value 0.7 divided by 180 and the value of the weight multiplied by 0.3 divided by 75. This gives us 0.7 over 180 gives us a weight W1 of 3.8 times 10 to the minus 3. And the value of weight 2, 4 times 10 to the minus 3. So actually, even if we gave the temperature an highest priority, in the end, the value of W1 for the temperature is lower than W2. So this choice of weights is not very easy, but we have anyway some advantage of it. So for instance, the advantage is that the function anyway is a scalar, so that any single objective algorithm optimization can be used. And this means that we can use genetic algorithm, deterministic algorithm, what we want, but actually this is something that is going to be very easy with respect to multi-objective problem. On the other side, on the drawbacks, since the weights have to be selected a priori, this choice will define which particular solution is obtained. This requires usually to run the scalar optimization many times. For instance, in the case of two objectives, like in a two-dimensional plane, the weight set defines an hyperplane with a given slope. This slope will bring us to one particular point on the Pareto front. So actually, this is another drawback that we will try to highlight in the literature material that we will introduce. Another way of going from multi-objective to single objective is the goal programming. Goal programming tries to find a place, a point in our configuration, a solution that is as close as possible as the theoretical best solution. We already met this concept speaking of the utopia point in the restaurants. If you remember, so in restaurant, having the cheapest restaurant at the highest quality was something that was not possible, okay, because either one is cheap or has a very good quality. So this utopia point is what we can say is our ideal point. So even if we can't get to the utopia point, we can try to minimize the distance of our configuration from this goal. And this process is what is called goal programming. So what is, again, we are going to look at the utopia point, that is the minimum value of f1 and the minimum value of f2 of the two objectives, and we'll try to find the point that is the closest as possible to the utopia point. This is something that can be, again, implemented by any scalar algorithm. This fuzzy definition of scalar criteria is using some particular property of fuzzy logic that is similar but different with respect to the usual Boolean logic. In Boolean logic, each statement can be either true or false, can be in the middle between the two. In fuzzy logic, we can have an intermediate degree of truthfulness in the sense that something is not crisp. It is not either true or false. You can have a degree of falseness or degree of truthfulness. So let's think about defining the set of average 8 person. There is not one single value of average 8, but we can think about 8 for a person is ranging from 160 centimeter to 180 centimeter, centered around 170 centimeter. We can say that for sure if someone is 170 centimeter high, okay, true that he or she is average 8. If one is 175 centimeters tall, then actually what it is not completely false, but there is a way to define the value of this function, that is the red function for 175 centimeters is equal to 0.5. So it is, in this case, 50% true and 50% false. But why do we need this kind of concept? We can use this kind of concept to try to define the degree of satisfaction of certain objective. So in our multi-objective optimization, we can have a particular way of defining some target about some particular value that our objective needs to satisfy. For instance, let's say that the force in one device should be more or less around 100 Newton. But it can be a little bit lower, a little bit higher, but it should not be that far from 100 Newton. It is maybe unacceptable if it is lower than 90, unacceptable if it is higher than 110, but in the middle there is a certain degrees of acceptance. This can be done also in another way, for instance, for weight for a particular device. The weight can be completely acceptable if it is lower than 50 kilos, can be completely unacceptable if it is higher than 100 kilos. In between 50 and 100 kilos, there is a certain degree that obviously is better if it is closer to 50. Now, we can define some criteria in our multi-objective optimization program and then use logical operators to combine this criteria. The AND operator in classical logic for two statements is true only if both of them are true. In fuzzy logic, what it is, instead of having either 0 or 1, here we have to intersect our membership function. So actually the green region in the graph tells us that there are some value along the y-axis that can be satisfying partly the red criterion and partly the green criterion. So in this case, if we have two membership functions, one for the red, for instance, is m sub a, and the green one is m sub b, and we apply the AND operator in fuzzy logic, is something like the minimum between the two functions. So for instance, it's something that multi-criteria can be expressed by the AND. Taking into account that all criteria are met, the logical result is true. So actually we reached our objective, like the goal, the utopia point. So optimization of degrees of satisfaction of different criteria can be expressed as the maximization or the minimization of all degrees of satisfaction of all the membership function m sub j, for j going from 1 to the total number of objective capital M. Each membership function expresses a well-known target in each objective, and in this way our scalarization does not need any normalization and weight. So actually it's something that can be more related to some designer idea about the problem that we want to optimize. Game theoretic approach. What we have here, we have the use of game theory concept, a very simple one, and we want to use the analogy between multi-objective and players in a game. Obviously, objective can be seen as players in a game. Each player wants to reach the best result for him or herself, and obviously his success is obtained at the expense of some other loss. Obviously, this is a concept of bargain. So how much are we open to lose? How much are we ready to gain? The result is a game. It's a way of selecting one solution, like in the restaurant picking problem, where we had a two-dimensional plane, where we had on one axis the cost and on the other axis the quality. If you remember, there was the possibility that someone, for instance, Uncle Scrooge, was trying to minimize the cost regarding on what the quality of the restaurant was, while instead Gladstone was trying to maximize the quality regarding on what the cost was. So who is going to win if they have to go and have dinner together? They can play, obviously, each one wants to have the maximum, but they have a penalty. If they don't agree on some point, they will get to the nadir point, that is the lowest quality and highest cost restaurant. And nobody of the player wants to get to the nadir point. So in this case, the Nash bargaining solution theoretically defines the best compromise on Pareto front. That is what was defined by the scientist John Nash. Theoretically, the concept is applying a maximization for each player of the distance from the disagreement point, so like the nadir point that we have shown before. Taking for each single objective the distance between a point u1 and the disagreement point, we try to maximize this kind of function, and in two dimensions like an hyperbola. So if we want to be as far as possible from the nadir or disagreement point, we can try to find on the Pareto front the point that maximizes the criteria, so the Nash bargaining point. So in the end, instead of having no agreement and going to the nadir restaurants, both Uncle Scrooge and Gladstone meet at some point that in this case is a fair way of defining a bargain between the two players. So in the end, we try to summarize the comparison of aggregation technique. All these techniques share the same target or combining different objectives in one single objective. This single function can then be optimized by means of any scalar optimization algorithm. There are some pros and cons for each of these techniques. For the objective weighting, we have on the positive side some mathematical property, then the solution will be on the Pareto front. On the negative side, we need the weights, and we try to show how this can be tricky from the little bit if we don't know in advance the problem. The goal programming, again, as a pro, it is find a scalar problem. So actually it needs to know what is the range of the variation of, and this can be also a problem with the shape of the Pareto front. On the fuzzy aggregation, we have again a scalar problem, and here we don't need to define weights, but we define clearly some criteria that we know in advance that we want to reach this target. And anyway, this is something that has to be defined a priori. Game theory approach. If the problem has some theoretical mathematical property, the solution is known to be on the Pareto front, and it has lower drawback as it can be used also in the many optimization problem. So thank you for your attention.